Welcome to the single photo tutorial. In this tutorial we describe perspective, inverse camera, constraints, control points, and surface draw. Photomodeler has special features that allow you to do projects using single photographs taken with an unknown camera. This includes photographs provided by third parties such as bystanders, media, and from historical archives. There are some criteria to using these single photos. In this segment, we will discuss photographic perspective and how it determines which images are suitable for use in single photo projects. Perspective refers to how the 3D world looks in 2D photographs. For example, a railroad track getting smaller into the distance is a perspective effect. First, we will look at one-point perspective. In this photo, the camera is parallel to the face of the object and the view is straight on. The horizontal and vertical lines of the blocks appear parallel. The horizontal lines on the top of the blocks, front to back, if we could see both of them, would vanish to a single point in the image. This means if we were to draw the points and extend them, they would meet at a point. This will be more obvious in the following images. In two-point perspective, the camera position is still level, but the object is rotated, resulting in views of two faces of the object. The horizontal parallel lines on the object are not parallel in the photo, but the vertical lines are. The horizontal parallel lines, if extended, all meet at one of the 2 points, hence the name two-point perspective. In three-point perspective, the camera is pointing up or down, as well as the object being rotated, and the vertical lines are not parallel either, so you get 3 vanishing points. As you can see, the more perspective a photograph of an object has, the more information can be extracted from it. Photomodeler's single photo capabilities depend on perspective in order to rebuild the unknown camera parameters. Photomodeler is unable to use photographs that have single-point perspective when the camera is unknown. These photos do not contain the information needed for Photomodeler to do its calculations. For photos that contain two-point perspective and where the 2 vanishing points can be extracted, Photomodeler is able to solve for the focal length of the unknown camera. For photos with three-point perspective and where the 3 vanishing points can be extracted, Photomodeler can solve for focal length and principal point. Principal point is useful if you are not sure if or how the image was cropped. To use Photomodeler for single photo projects from unknown cameras, you must have photographs with 2 or 3-point perspective. If the camera parameters are known, then some work can be done with single-point perspective photos. Once you are familiar with perspective, you will be able to determine whether or not you can perform a Photomodeler project with your single photograph. We will start a new project using a single photograph from an unknown camera. We click the New Project button from the toolbar and choose the Standard Project option. We click Next. We review the project steps and click Next. We choose a measurement unit of inches and enter our guess of an approximate size of 1.5. We click Next. In the Camera Wizard, we choose the option called Unknown Camera for inverse camera forensics. This is the option to choose when you have a single photograph and you know nothing about the camera. When this option is chosen, the camera parameters are solved for by Photomodeler when the project is processed. We give the camera the name Unknown Blocks Cam and click Next. We only have a single photo, so there is only one focal length. We click Next. The image came from a digital camera. We click Next. We have the digital image file. If we did have a photographic print, we would choose this option and then enter some further information that would help Photomodeler determine the pixel size. We click Next. This next pane tells us that the Camera Wizard is assuming the image has square pixels. This is generally a good assumption when using digital cameras. We click Next. We don't know what the focal length was, so we leave it the default setting of 9 mm. We click Next and view the default camera parameters that were set up when we chose the unknown digital camera option. We click Next and press Add Remove Images. We select our single photo from the Single Photo Project folder and import it into our project. We click OK, and we get a message telling us that because we are using inverse camera, the focal length flag has been set. This means that focal length will be solved for when processing. We click OK. We see our single photograph imported and click Next. We have completed the setup, so we click Finished. We open our single photograph and review it. We can see that this photograph has two-point perspective, and therefore it is acceptable for use in a single photo photomodeler project when we want to solve for focal length. We right-click over the photo and choose Photo Properties. We look at the inverse camera processing section, which we have seen before but haven't described in detail. The options here are only used when you don't know anything about the camera used to take the photograph. Certain information about the scene, though, must be known in order for inverse camera to work. This known information is called constraints, and we will be using them in this tutorial. Using the single photo and constraints, we can solve for focal length of the unknown camera. Focal length is usually the most important parameter to solve for. Principal point, which refers to the center of the imaging area, can be solved for only if the photo has three-point perspective. This is important if you think the image has been cropped. Format aspect ratio refers to whether the pixels in the camera and scanner are square. This option is not usually needed, but it is available if you suspect non-square pixels. More details about all three options can be found in the Help file. We leave the focal length option checked and exit the Photo Properties dialog. We will now begin working with our single photograph. We can solve for focal length in this two-point perspective image, but we need to use constraints. Constraints refer to known information about the object in the photo. Constraints come in two forms in PhotoModeler. One is called simply constraints, the other is called control points. First, we will work with the constraint mode. We maximize our photo and click Zoom to fit. First, we will use the line tool to draw some lines along the outline of the box. We then use the Alt-Zoom tool to adjust the point positions. It is very important to mark accurately in these single photo constraint projects. Next, we click the Constraints Mode button from the toolbar. The Constraints toolbar appears, and the cursor changes to reflect we are in Constraints mode. There are a number of ways to create constraints. First, we will click the Get New Constraints button, and that opens the Constraints Properties dialog. The drop-down list shows the different constraints available for single photo projects. We choose the constraint called Lines, Edges to be horizontal left to right, x-axis, and click OK. It appears in the toolbar as the active constraint. Using the Shift key, we then select all the lines that are horizontal left to right. The selected objects are highlighted in red. We then click the Add to Constraint button. The other way to add constraints is to select the items first, such as these vertical lines. And then click the Get New Constraint button. We then choose Lines, Edges to be vertical. Notice that in the Constraint Items box, the lines we had chosen are now listed. We click OK. Next, we will add a third constraint. We right-click and zoom in for a closer view. We select these lines, and click Get New Constraint. We choose Lines, Edges to be horizontal front to back, y-axis, and click OK. We will review each of the constraints we have added. In the Settings tab, we turn on Thick Lines so we can have a better view of the constrained objects. First, we choose All Constraints from the Toolbar drop-down list. All the constrained objects on the photo are highlighted in green. If we choose Lines, Edges to be horizontal left to right, x-axis, those constrained objects are highlighted. We select Lines, Edges to be vertical, z-axis, to view those constrained lines, and Lines, Edges to be horizontal front to back, y-axis, to highlight its constrained lines. We turn Thick Lines off. The constraints we have added to the image provide enough information for inverse camera to solve the project. We click the Process button from the toolbar to bring up the processing dialog. We look at the Audit Summary section, and there are no suggestions provided. There will sometimes be comments and suggestions listed here describing how well the constraints will solve, or suggesting that you add more constraints. The processing steps show that one photo will be oriented. There is no global optimization stage in a single photo project, and constraints will be processed. We click Process. Processing is very quick in single photo projects. We get a successful process and we click OK. We notice now that the title bar indicates it is oriented. We select Project Cameras to review the solved camera parameters. We click Modify and review the parameters. Looking at focal length, we see that the solved number is just over 6 mm. Remember, the initial focal length set in the camera wizard was at 9 mm. Inverse Camera used the constraint information to solve for the correct focal length. The other parameters remain at the default numbers. Note that this box is checked here at the bottom to indicate this camera is an inverse camera. We exit the dialog. We open a 3D viewer to view the results. We choose Points, Lines and Camera Stations and click OK. We view the solved camera station and the lines that were marked on the photo. This looks like a reasonable solution, so we will continue. Like in a regular photomodeler project, we can add to this project. Next, we will add surfaces to the model. We minimize the 3D viewer and add surfaces using the photograph. We choose the Path Mode Surface tool. In Path Mode, we click on points in a path. We end the path by clicking again on the point we started with. Other objects, such as lines and edges, can also be included in the path. We create surfaces for each of the faces of the blocks. As we noted in the earlier tutorials, surfaces do not appear by default in photographs since they are full 3D objects. With more screen space, we could have the 3D viewer open at the same time as we create the surfaces, and we could see them as they are added to the model. This could also be done with surface projections, but for clarity we leave them off for now. We reopen the 3D viewer window, and in Options, we turn on Shaded Surfaces and turn off Camera Stations. We review, then go back to Options, turn on Fast Textures, and review the model. This completes the constraint method for our single photo project. We started with a single 2-point perspective photograph. We set up the project as an inverse camera project, then added constraints to the marked lines on the photo. Inverse Camera was then able to solve for the unknown camera's focal length, and a 3D model was created in PhotoModeler. Another method for solving unknown camera single photo project is through the use of control points. We will start with a project called controlstart.pmr, which can be found in the single photo project folder. We have already set up this project using the setup wizards, using the same settings that we used in the first constraints project tutorial. A few lines have been marked in the photograph already. We have done no other work, and we can see that the photo is not oriented yet. Next, we will mark the control points on the photo. Control points are known XYZ coordinates that we can match to objects that appear in the photograph. This information can be acquired by doing a survey of the scene using PhotoModeler or by using another measurement technology. The control point data can then be stored in a text file or DXF file, which can both be imported by PhotoModeler. We select Marking Mark Control Points mode. This brings up the Control Points dialog. By default, the Control Point dialog opens with this preset list of control points consisting of a set of coordinate axes. We can see the control points in a list view or in 3D view. The control point editor can be accessed by clicking the Modify button. The control point editor allows us to do various tasks. We can select points and view and modify the coordinate information. We can add new control points by clicking Add and entering known XYZ locations. We can delete points from the list as well. Here we will delete the 4 default points and click OK. We have already created a text file with our control point information and saved it in the project folder. First, we will open it up in Notepad and view the format of the file. There are 4 columns in the file: point ID name and the XYZ coordinate numbers. The units are in inches. We close Notepad. To bring the control points into our project, we click the Import button. In the Import Types section, it lists the various types of control files we can import. We choose the text file option. In the Importing Units section, we choose inches. Here we choose Do Not Adjust these controls. This means that the XYZ control point data will not be adjusted during processing. For very strong photo modeler projects, where the project is as accurate as or more accurate than the control points, you might want to leave this box unchecked so the points will be adjusted. This is discussed more in the manual and help file. We click Browse and open the blockscontrol.txt file. We click OK, and the control point names appear in the Control Points dialog box. We click on the 3D view, and we can see the block shape of the control point data. In the list view, we can select a point, and the XYZ coordinate info appears along the bottom. We want to view the list in the order we saved them in the text file, so we turn off the alphabetical list option. We select the first point with the name PFTL. The IDs can be named whatever you like, but they should be named so the names assist you when identifying the points. In this case, we named it PFTL, which is short for P block front top left. This will help us as we mark the points in their proper locations. We move our cursor into the photo window, and you'll notice that the cursor shows we are in control point mode with the triangle and dot on the end. We move the cursor over this point and click. The point mark changes to a small triangle indicating that this point is a control point. Control points can be marked on existing points or marked as new points. Once the control point is marked, the next point in the list is highlighted. This one named PFTR stands for P block front top right. We mark the point there. Next we mark the bottom right point, then the bottom left point. The next point named PBTL stands for P back top left. We mark the point, then mark the back bottom left point. The remaining 2 points cannot be seen in the photograph, so we skip them. We close the control point dialog box and click the Process button. There are no suggestions in Audit Summary. The processing steps tell us it will orient the single photo. We click Process. The project solves and we click OK. We select Project Cameras to review the solved camera parameters. We click Modify, and we can see that the focal length solved at just over 6 mm, similar to the number we received in the Constraints project. We click OK and Close. We open a 3D viewer to view the results. We turn on points, lines, and camera stations and click OK. We have solved for the camera position and the 3D data provided in the control point file. For a particular type of project called camera perspective matching, this result is all that is needed from the project. In perspective matching, you have some known XYZ data of an object, and you're just trying to solve for the camera's focal length and its position. This type of project is used often in the film and animation industry. Here we want to add detail to the project and make it more complete. We have only the one photo, therefore we can't mark and reference further points. We also do not have any more control points, but we are still able to add to the project using some special tools. We make a few assumptions. We can safely assume that the face of the J block is on the same surface plane as the P block. This allows us to use the Surface Draw tool. To use Surface Draw, we first must have some surfaces marked. We click the Surface Path tool and mark the face of the P block. We switch to the 3D viewer window, turn on surfaces, turn off camera stations. We hit Reset and use the viewer controls for a better view of the marked surface. Back in Options, we turn surfaces off and turn Surface Draw on. This will provide us a better view of the Surface Draw marks as we add them. We tile the windows so we can see both the photo and 3D viewer. We use the scroll bars for a better view of the blocks. We then select Surface, Surface Points Line Mode. Our cursor changes to Surface Draw Line Mode. We know that a surface has been created on the face of the P block. To view the surface on the photo, we turn on Surfaces Projection. Surface Draw allows us to mark points on the surface plane, and they will appear immediately in 3D. Surface Draw does not require referencing. For example, we mark along the outline of the P. We zoom in for a close view and start marking. The points appear immediately in the 3D viewer. We will just model a rough outline. If we rotate the 3D view, we can see that the points all lie perfectly on that plane. Surface Draw also allows you to mark outside of the surface. We can do this as long as we mark our first Surface Draw point within a valid surface. We reactivate Surface Points line mode. Here we start with a point within the surface of the P block, then we can continue the Surface Draw outside that surface and model the J block. We are making the assumption that the J block face is on the same plane as P block face. We review in the 3D viewer and study the results of the extra Surface Draw. Next, we will use the Surface Draw Curve mode. We zoom in on the photo so we have a closer view of the J. We start by marking a point within the surface of the P block, and then move the mouse over to the J and start marking along the curves of the letter. Again, the Surface Draw marks are automatically 3D, and they can be seen in the 3D viewer as soon as they are marked. We finish the curve and review the model in the 3D viewer. Here we have shown a simple example of how single photo projects and Surface Draw can be used. The same principles can be applied to real-world projects such as modeling a building or a road scene. For a building, a facade could be modeled from a single photo using constraints. Details of the facade could be added using surfaces and Surface Draw. For a road scene, control points could be acquired from a survey of the scene, and surfaces and Surface Draw could be used to mark evidence or trace skid marks. This completes the single photo project tutorial. We have worked through the topics of perspective photography, inverse camera, constraints, control points, and Surface Draw.